Welcome to the lecture series on probability theory and stochastic processes. In this lecture series, we are going to study about fundamentals of probability theory, subsequently followed by the concepts of random variables, random processes, along with the application of these random variables and random processes to linear systems. In this lecture, we fundamentally concentrate on what is the necessity of probability theory, and then learn few definitions. Later extend our this introduction to probability theory to other aspects. To begin with, why should we go for probability? What is the role of probability? Let us know first of all. Everybody knows clearly that in real time, everything is uncertain. We cannot exactly define what occurs in real situations. Suppose a question is being asked, what is the temperature at tomorrow, 12 p.m. asked. Or someone asked, what is the scope of or probability of getting a cardiac arrest at the age of 40 years? Or what is the size of the raindrop in weather forecasting? While designing a rifle, the question can be asked, up to what extent you are sure that this will hit the target effectively? In all these questions, and so many so far, many more questions, we cannot confirm the event outcome. So for completing the system design, we need to have some conclusion about the outcome. We cannot simply say, I cannot predict the outcome for this corresponding task performed, which will be affecting the complete design. In all such cases, numerous, not only given examples only, in numerous cases, definitely a situation comes where we have to approximate the task or question asked and take a necessary design. Let me take a particularly one communication aspect. I am a communication engineer, for example. I've been asked to develop a mobile tower or cell tower. Okay, so simply designing a cell tower, okay, that is another thing. What is the strength of the signal radiated from the cell tower? How can we exactly say? Sometimes frequently we are going to encounter that our calls get frequently dropped. We use it to inform to our friends that hey, our call is intermittently cut. We will call you later. This is mostly felt by many of us. So in such situations, what the service provider should do? Should he continuously transmit higher signal strengths? Always not safe also. So the signal strength determination may be some extent relying on the environmental conditions prevailing in the coverage area. The traffic may affect the signal strength to some extent. The weather conditions, the obstacles in the environment, etc., are going to predominantly affect the signal strength, thereby causing the mobile call to be lost. In such situations, I have taken one example for a communication engineer perspective. Similar is the case for any other applications. So, to conclude, in these application point of view, in most of the real-time scenario, we assume something and then proceed for the associated task. Suppose a faculty is taking a class in the classroom. Any faculty, not a single faculty, how he goes into the classroom, he assumes that all the faculty are, sorry, all the students will listen to the class, and with that optimal thought only, optimized thought only, I should say optimistic thought, he is going to enter to the class and take the class. If he initially have no such idea, then no output can be delivered. So this assumption, just I have taken one example, this assumption of this may happen or that may happen, this is the value, at this instant that may occur. Like all these assumptions are useful in the system design and maintenance. And such assumptions are having their roots in the probability. But then let me start defining what is probability. Probability is a generally a numerical quantity. Okay, probability is a numerical quantity assigned to the chance of occurrence of one specific outcome. So to begin with, let me just mention what are the key factors in the probability theory. Basically, probability theory is going to have three fundamental concepts. In its base, three fundamental concepts. They are correspondingly, the first one is an experiment. The first one will be an experiment, and second one will be the sample space, and third one will be an event. These three predominantly define the probability theory that is going to be used. One being the experiment, second one being the sample space, and third one being the event. To begin with experiment, the meaning of experiment generally is performing some task. I am interested to know the temperature, one experiment. I'm interested to know the heart beating rate of a person. I'm interested to know the outcome of taking some value in diode characteristics. I'm changing the voltage. What is the change in the corresponding current, etc. So in simplified terminology, experiment corresponds to performing some task, which is applicable to any case. In the earlier communications example, the design engineer may be worried about how the signal strength fluctuates with respect to distance. So what do? I am going to measure the signal strength. Okay, so that is the predominant and most important thing to be remembered in the probability concepts. There is an experiment. It means that we are performing some task. Then, okay, so experiment means performing task. Then what happens? Every experiment has sample space. What is the meaning of sample space? Sample space is the set of possible outcomes. For example, take the case of throwing a single dice. In such a case, the sample space can be represented as 1, 2, 3, okay, 4, 5, 6. Why? Because a dice has 6 faces, each numbered from 1 to 6. That is one experiment. The another experiment can be, I have tossed one coin. So what are the possibilities? It can be head or it can be tail. Like many. If you have observed here, generally we represent the sample space with a capital letter, and these are the outcomes of the sample space or elements of the sample space. The elements of the sample space are nothing but the outcomes of the respective experiment. Okay, So generally, suppose one more thing, I want to measure the weight of a particular batch of students. So sample state will be a continuously a real number may be varying between roughly 50 kgs to etc 70 kg approximately. If I say any value is possible, so this is the possible number. I can represent as 50 less than or equal to say weight less than or equal to 70. So this is the sample space for the experiment of measuring the weight. So what is the task in such a case? I want to measure the weight is the task, and the set of outcomes, that is sample space, can be any value between 50 to 70. That is the meaning of sample space. Okay. And what about the event? What is the difference between an event and sample space? To be precise, an event is going to characterize the behavior of sample space. Okay. If any experiment, not exactly sample space, the event, okay, events are describe the behavior, or in other words, nature, behavior or nature of the experiment. Behavior or nature of the experiment. That is one way to define. Second way is an event is a subset of, it is not a complete one, we can say, it is a subset of sample space. Subset of sample space. Suppose for the experiment of throwing a dice, actually the sample space is 1, 2, 3, 4, 5. For this case, I can define an event such that it consists of numbers. Okay, numbers between, I just give some notation, x less than or equal to 4. If you say this will be equal to 1, 2, 3, 4, what it means? The event of getting a number less than or equal to 4 is a subset of the given sample space. So in such a manner, the events are going to describe the given experiment more effectively than the outcome itself. Like in a class, suppose if I talk about percentages of students, okay, suppose the task is experiment is percentage of students in the examinations. Definitely, it is a real number, right? It is a real number. Starting from, I take roughly nearly 40% to, this is P percentage, to nearly say 80, let me call. The sample space for the experiment, knowing the pass percentages or marks of the students is sample space 40 to 80. So within this, I want to know further, if I define an event on this, I want to know, okay, let me say an event B. What is event B corresponds to? Okay, marks less than 80, or pass percentage or percentage of marks less than 60, I say. Okay, 40 to 60. How many number of students got marks between 40 to 60 can be one event. So from this small example, we can be able to know what exactly the event can be. Like the example of throwing a dice, or the example of knowing the percentage of marks of students, we can further define subsets, that is events, to describe them. So these 1 and 2 and 3, that is one, that is experiment. One more time. So what is the thing to be concluded up to now? Probability basics, or probability has its roots in these 3: experiment, then sample space, okay, followed by an event. Once these 3 things were known, then what exactly probability? How to define probability? Probability can be defined in 2 different ways. The first way being the axiomatic approach, we call generally. Okay, the first way can be the axiomatic approach, and the second can be the relative frequency approach. So probability definition can be carried out Probability definition can be carried out in two ways. One is axiomatic, and second one is a relative frequency. These are the two ways to define probability. Okay. What is the meaning of axiomatic definition? Is axiomatic definition is not having any mathematical support. It is rule based. Okay. So let you briefly know first of all what is the meaning of axiomatic definition. As I just mentioned now, axiomatic definition is a rule based. There is no sufficient mathematical support for that. According to this, probability can be first definition of a probability according to axiom. It is defined as a probability of any event A. Let me call an event A. Suppose say an event A is there. So probability of any event A or B, whatever you can call, is always a non-negative quantity. I think it's clear. What is the meaning of A? A is certain event, which is subset of the sample space. So it will be always non-negative quantity. So how can this be justified? Suppose you have been asked, you have been told, okay, when a question is asked, when a should person may come, or will a person comes to certain place? The answer can be will come or will not come generally. So will come means surety is there, value 1. He won't come means 0. So between this only it will vary. Got it? I think so. You got it. So probability of any event is always a non-negative quantity. We assign only non-negative numbers. That too, that non-negative numbers also too, it is going to be between greater than a 0. That's it. And second definition, probability of P of S is always equal to 1. What is the meaning of this one? P of S. What is it's a sample space. So whenever an experiment is performed, whenever a task is performed, according to this axiom, definitely there will be an outcome. There is no experiment in anywhere where experiment is performed and outcome is not there. A coin is tossed, head or tail. A dice is thrown. 1 to 6 are the numbers. We can get any number. A person's weight is measured. You may get any real number, etc. So the meaning of this axiom, particularly P of S equals to 1, is definitely there is an outcome. Definitely there is an outcome for any experiment. This is the meaning of P of S. Okay. So then further, some more from this first and second axioms, we can have a third one also that can also be obtained. Suppose, say, for example, before I proceed, complementary event. A is an event. We can also define another definition, probability of a complementary event. What is the meaning of complementary event? If A event is going to occur, its complementary is 1 minus P of A. This is going to be a complementary event. Okay. So, like these axiomatic definitions are going to define the probability through rules. That is the first definition of probability. It is a non-negative quantity. Whenever an experiment is performed, definitely there will be an outcome. That is, probability of sample space is always a unity. That is occurring na any one of the event may occur. Then the another definition is based on relative frequency. This definition, as the name indicates, relative frequency definition depends on whenever an experiment is performed, how many number of times a specific event may occur. It's generally called as a number of favorable outcomes. For example, take a case. We are picking a card from a deck of 52 cards. Let me just say one example and then proceed. We are picking a card from a deck of 52 cards. Okay, so what is the probability that the card being a jock? If this is asked according to relative frequency definition, the answer will be definitely 4 by 52. 52 is the total number of cards. What about the 4? In a deck of 52 cards, there are 4 jocks. So this corresponds to number of favorable outcomes of event A. What is event A? Getting a jock. So according to this relative frequency definition, P of A equal to NA by N. What is NA? Total number of, or number of, I should not say total number of favorable outcomes for A divided by total number of outcomes for the corresponding experiment. Total number of experiments. Okay, so examples are many. Say, I have thrown one dice. What is the probability of getting a 1? 1 by 6. I have tossed a coin. What is the probability of getting a tail? 1 by 2. Why? Because when a coin is tossed, either head may come or tail may come. Only one is a favorable outcome. So the value will be 1 by 2 or 1 by 6 based on the experiments. So this is the relative frequency definition of the probability, which is, once again I write, which is the most popularly used. Why it is popularly used? Because there is a strong mathematical base. No, for any experiment we know how many number of outcomes. For the same experiment we can know favorable, means how many number of times an event may occur. So P of A equal to NA by N can be termed as the relative frequency definition of probability. For an example, as I have already mentioned there, okay, what is the probability of a spade when a card is picked? What is the probability of a spade when a card is picked from deck of 52 cards? Okay, we all know. Okay, in a deck of 52 cards, there are 13 spades. If I call the event of getting a spade as B, okay, if I call the event as B, what event? Getting a spade, then probability of B equal to 13 by 52. Okay. Because of this mathematical support only, this relative frequency definition is popularly used. Okay. So till now, we're talking about probability definition using relative frequency approach and axiomatic approach. Now, let us slowly go further to next definition called as joint probability. Joint probability. This probability is going to give information about the chance of joint occurrence of multiple events. Not a one event, okay? How much extent two different or three different events can occur together, that is called as joint probability. Suppose say there are two events A and B, for example, okay? Then the joint probability can be represented as P of A intersection B, or I can simply write P of AB equal to NAB by N. As usual, what is NAB? NAB corresponds to number of times event A and B occur together by total number of possible outcomes. Okay. So this is the definition of joint probability using relative frequency approach. Okay. Now let me take an example. Okay, same example of deck of 52 cards. Okay. What is the probability of what is the probability of getting a spade king? What is the probability of getting a spade king? So in a deck of 52 cards, we know that P of AB equal to 1 by 52. Why it is 1? Because in a deck of 52 cards, 52 total number, a king and a spade intersection only 1. So that is 1 by 52. So this is the way we can be able to define the joint probability. Joint probability gives information about joint occurrence of multiple events. Okay. Then let us go further. Basic definitions only. Conditional probability. Conditional probability. In certain instances, no. Okay, generally, occurrence of one event may exclude the occurrence of other event. Otherwise, occurrence of an event may affect the occurrence of another. Most of the time. Okay. So in such cases, we need to know what is the conditional probability. So let it be defined as the condition. Let there be two events A and B. Okay. In such a case, the conditional probability can be defined as probability of event A once B has been occurred can be given as probability of A intersection B by probability of B. Okay, or simply writing P of AB by P of B. A and B are two events. We have already seen. What is the meaning of an event? We have already seen. And further, I hope that you are having the knowledge about what are the different types of events, like mutually exclusive events. No, at this instant, I want to add a couple of terms. Yeah, events can be mutually exclusive. Events can be statistically independent. Statistically independent. Okay. So the meaning of mutually exclusive events is occurrence of one event is going to remove the possibility of occurrence of another event. They are mutually exclusive. If one event occurs, the another event cannot occur. Example, I have tossed one coin. I got a head. So the possibility of getting a tail is no more. That is the example of mutually exclusive. Coming to statistically independent events, these events are not interdependent. Occurrence of one may not affect the occurrence of the another. Such a case, they are called as statistically independent events. It's not that mutually exclusive and statistical independence are same, never. Take the case of throwing two dice at once. Okay, two dice are thrown at once. Okay, so I have got one number, suppose say 2 on the first dice. It does not guarantee that the another dice may get 2. That's it. That is the meaning of statistical independent. Getting a 2 on the first dice will not affect getting a 2 on the second dice. Statistical independence. So the events A and B, as I am mentioning here, they can be mutually exclusive or they can be statistically independent. Suppose if two events are statistically independent, then correspondingly the probability of A intersection B can be mentioned as probability of A into probability of B by probability of B. This is probability of A itself. Simple. Why? Because occurrence of event A is not depending on occurrence of event B. So in such a case, the conditional probability is equals to the probability of A itself. Okay, so in the next lecture, we continue with the conditional probability and then talk about the fundamentals of random variables based on the probability concepts. Thank you.